Our next speaker is Dustin, who is going to tell us how Shamir secret sharing behaves in the face of side channel attacks.
Okay, hello. So yes, that's what I'm talking about. So let's start by just setting things up, because normally we use secret sharing with polynomials, but in this context we're going to do it all with linear algebra because that makes it a lot easier for us to take a whole bunch of Fourier transforms. Largely this is going to be based off of the same kind of proof that Klein and Komargarsky used in their breakthrough paper last year. So we're going to choose some security parameter n. We've got our secret s that we're distributing among people. We choose our polynomial, and then we're taking p of 0 to be embedding our secret. So it's a pretty standard setup. But then what we're going to do is we're going to choose a vector of its coefficients, and that will let us sort of translate this polynomial into linear algebra space. And then to each party, we're going to send the evaluated share, I, pi, and from there, of course, we can reconstruct the secret by sort of looking at all these points and rebuilding our polynomial. Once again, though, we're going to use some linear algebra, and we're instead going to construct these vectors Li, which just have the property that Li dotted with x is going to give us p evaluated at I. So, of course, we have security, where any tn minus 1 shares being totally corrupted gives no information, but if we retrieve from tn shares, we get our secret back. So, as you can tell, my slides are not a whole lot of fun, but and there's going to be a lot of like nasty things written up on the board. So largely, I'm going to sort of put nasty things on the board and then try to give a little intuition behind what the heck these nasty things mean, if you struggle with Fourier analysis like I do. So our definition of leakage, right, is that we have these 1-bit functions, and the 1-bit function gets to look at each of the shares sent out. Well, a function looks at each share and then reports back to the adversary, okay? So Klein and Komargarsky in their 2023 paper got leakage resilience for t greater than 0.688. In this paper, I got t is greater than 0.668, which, as you can tell, is not a dramatically huge improvement in security. But somehow it takes a fair bit of work, and I'll talk about like the two kind of in the first part of the section, I'm going to steal an idea from additive combinatorics, and the second part of this talk, I'm going to show how we can sort of play these S's against these choices of sets that we're going to use in our proxy against each other in an interesting way. Okay, so the analytic proxy that they found is this FS object, where they're summing over somehow the products of all these leakage functions. So what this Fourier transform, this FS hat of L naught means somehow is if you take a whole bunch of your leakage functions and you multiply them all together, you would hope that these have some kind of structure that correlates well with the secret, right? Because you're trying to recover the secret as the adversary. And so if you're the adversary, you want to construct these functions where you can find some kind of structure that you can exploit to get information. So somehow this Fourier transform is really a measure of the structure of each of these FS objects, which corresponds with the amount of information gathered. So as a result, it makes sense to directly try and bound, how big can these FS objects be? How much structure can they have? And so this is some linear algebra saying that basically these FS objects are composed of a whole bunch of largely linear independent objects. And so we can turn the Fourier transform into a convolution over these linearly independent objects, and then we can apply Holder's generalized inequality, which basically means we just take a Cauchy-Schwarz type inequality twice here. So what does this final thing I've written down as a lemma mean? Basically, it's a measure of how much structure each of these FIs individually have. Okay, so the L infinity measures sort of their total structure, whereas this FI and an L4 norm measures their sort of average structure somehow, with a lot more weight being given to the peaks. So in their paper, Klein and Komargarsky used this sort of same technique, which is what we're trying to replicate here, except they used an L2 norm, because an L2 norm of a Fourier transform you can Plancher L and you have very good information about. But we're going to steal a 2001 result of Lev from additive combinatorics, which says that if you're measuring structure of Fourier transforms and that kind of stuff, of course, Fourier transform, the L2Q norm of Fourier transforms is maximized by maximally structured functions. So in other words, if we want an upper bound, we can replace our sort of arbitrary FIs with these very well-defined, incredibly well-structured functions, and that allows us to explicitly compute this upper bound K2Q. And I don't think writing out that sum is particularly helpful, so here's a perhaps more helpful graph of what K4 looks like. So as you can see, it sort of starts off at this large value, and then it dips down as this mean gets larger, and then eventually, as your mean of your leakage function gets larger, this norm gets larger as well. And that's basically because your Fourier transform evaluated at 0 is the measure, sort of your mean, and so when your mean is very large, your L4 norm becomes large as a result somehow. So basically what we're saying here is that your L4 function, there's sort of two big cases for your L4 norm. Either your mean is small and things basically are just this very well-structured function, or your mean is large. And if your mean is really large, what that means is that your leakage functions basically only ever output 1, right? They never output -1. And so somehow you aren't getting very much information from them. So Klein and Komargarsky were able to sort of run this induction argument where they say, you know, if your mean is large, then you aren't getting very much information, and so we can almost ignore that function. And then you just induct down somehow. So we'd like to do that with the L4 case, but things are not as nice in an L4 norm somehow. So instead we sort of get 5 different sets that we're looking at. We get the set that behaves like mean zero functions. We get the set where they're close enough to mean zero functions that we won't worry about them too much. We get the set where really we can't do anything nice with them. We can't run this induction argument, but we also can't say that they act like mean zero functions. So somehow then when mu is large, we sort of run an analog of this induction argument, where if mu is sort of like only kind of large, we run a not very effective induction argument. But if the mean is really large, we get to imitate this induction argument and run it all the way through. Whew, okay. So now we go back to the induction argument of Klein-Komargarsky, which says, right, if you have, now they actually don't need this because somehow in their paradigm, it makes sense for the adversary to always choose mean zero functions. But actually using their argument, if you have these functions with large mean, you actually get a lot of extra gain. And so basically in the last part of this segment to establish our L4 type bound, we play this idea of, in the L4 type bound, you want everything to mean zero because these large mean functions mess with your induction. But in the L2 type bound, you actually get really, really strong induction on things with large mean. And so sort of playing these two bounds that you get against each other, you say, well, the adversary can't choose many large mean functions or else you get a good L2 bound, but they can't choose few or else you get an L4 bound. And as a result, so the original bound of Klein-Komargarsky was that they got a 2 over pi to the t minus an, where sort of a is the number of functions that you're t plus a is the number of functions you're clumping together, whereas we get 2 over pi to the t minus 0.66 an. So we get a slower rate of decay in this kind of bound. And somehow you shouldn't expect to push this induction argument too much further than t minus 0.53a, because there's a 2 that if later on you're curious, you can flip back to the slide where I define K2Q, and there's an extra 2 in there that's floating around somewhere in all of your L norm stuff. So as you run this argument, you can't really hope to get rid of this 2 to the an. So if that lost you, we're sort of restarting and getting on to the next part of the argument, which is we're going to average. So I just did things sort of as a uniform bound on fs hat, but now it makes sense to say, well, we have all these different subsets S that we're like taking Fourier transforms over. Can we somehow play them against each other in an intelligent way? And the answer is, it turns out, yes. So here I'm defining this vector lambda of t And really what lambda of t is as I said, this Fourier transform is somehow a convolution. And so this lambda represents a parameterization of, says, how can you represent the zero of your polynomial in terms of all of your other points that you're looking at? And that's really all lambda is saying, but it's saying which of these parameterizations maximizes some set S tilde. And so then what's going to happen is we say, well, if I choose one set T with like my S prime and my S tilde, I choose another set T, and these two sets are too close together, my parameterizations have to be very different. And I get that from the linear algebra. And because they're very different, sort of any structure that appears in one can't appear in the other one. And so now we do a bunch of more functional analysis stuff. But really what we're saying is if we average over this set T and we look at all these different choices for our FSs, we really can't see the same peaks appear nearby. And that lets us take that lets us turn these things and say, well, all of these choices of T are different choices for this phi, as you can see in the bottom right. And so we're somehow summing over just the L2 norm of our Fourier transform of Fi, and that lets us safely apply Plancherel. And Plancherel is very nice because we're working with the Fourier transform of an indicator function somehow. And that lets us just drop our entire L2 norms, and we get this resulting bound. So this bound is undercounting because somehow we've split our normal set S up into this S prime and this T object, and we're averaging over T, right? And so somehow averaging over T introduces a lot of extra summing that we don't want to do. So we can just count, how many ways have we parameterized this, how many ways is it actually supposed to be parameterized, and then we normalize it all out. So just for a little context, and then I'll be done. This argument, this averaging argument, works very well when you're looking at these FS objects where they're very close to not doing anything. So this FS doesn't give any information if the size of your S isn't at least Tn, because then you're running into all of your, basically the security that comes with Shamir secret sharing. So this gives actually pretty good bounds when you're looking at FSs that are right near that threshold. And somehow but it trails off pretty quickly because we have this parameter k that I haven't worried terribly much about talking about. But this parameter k can't be well defined somehow when you get very far from the threshold. So it'd be interesting if you could figure out a way to get this parameter k to go further out. But somehow I think you're better off looking at the Fourier transform and trying to get some improvement there. So thank you for your time.
Do we have any questions? Yes.
So I wonder what would be your conjecture for the right bound, and also can you relate this thing to some natural property of the Ritz-Solomon codes, I don't know, the weight distribution or something like this that coding people may have thought about?
So I think, so what I'm doing is a purely functional analytic argument at some level, and so we have this triangle inequality that we're taking that goes inside this convolution, right? And a purely functional analytic, so I want to be clear, if you do some Fourier analysis to get additional improvements, I think you could get past it, but a purely functional analytic, I sincerely doubt will get you past the t equals 1/2 threshold, because there are these flat Littlewood polynomials that are, basically what it says is that they're not too small anywhere, and so when you just sum up over all the possible counts, you're going to lose in this triangle inequality once t equals 1/2 if you take that triangle inequality. In terms of coding theory, I'm not as well versed on that, I'm afraid, so I don't have any useful commentary for you.
Thank you.
I also had a very quick question. Your bounds decrease exponentially, right? Like with, they converge exponentially fast with the number of parties. Are they still meaningful for like a very small number of parties, provided the threshold is like the right one?
I think that is unlikely. I'm not totally confident, but most of it is, yeah, we're getting exponential decay. I've suppressed some terms here that come from error terms and that come from the original sort of analytic proxy of Klein-Komargarsky. And those terms have sort of a polynomial and p attached to them. And so I suspect that if your p is sort of large in comparison to your n, but not like too large, it's not clear to me that you would do very well. I think I'd have to sit down with a pen and paper for a little bit. So if you want to ask me that again later when I've had time to actually look at the numbers, I'd be happy to talk about it.
Okay, thank you. And thank you for suppressing some details.
Yeah.
With that, we can thank Dustin again. And